Welcome to our lesson on properties of two tangent lines to a circle. This is a continuation of the prior lesson in which we looked at the relationship of one tangent line to a circle. Our objectives today are to investigate the properties of a circle and the two tangent lines to a circle at points on the circumference. Also, we'll be solving problems using the properties of tangent lines to a circle, as well as the quadrilateral that is formed from those lines. Here is our theorem. The theorem states that tangent segments to a circle from the same external points are congruent. In other words, if we look at the segments, and we'll call this one, let's give these all a name, so let's call this point R and point S. So if we look at the segments RP and RS, the theorem states that those are congruent. But we're going to set about proving that. So, segment OP in this example, which is right here, and segment OR, which is right here, intersect at right angles, which we know that from our prior lesson, right? So anytime a radius intersects a tangent, at that point of tangency forms a right angle. Okay, so if we know that these two angles are the same, we also know, and notice that I've drawn a line down here in the middle to form two right triangles. Because what I'm going to do is compare my right triangles. Well, this line in the middle is the same line for both triangles. The reflexive property says that segment SO is congruent to segment SO. So if we look at our triangles SPO and SRO, we know these are the same triangles by the hypotenuse leg congruency shortcut. If you remember studying congruent triangles, there are certain shortcuts that can help us to determine if two triangles are congruent. The hypotenuse leg congruence says that if the hypotenuse and one other leg are congruent, which we have this center line SO, which is the hypotenuse on this upper triangle SPO, well, obviously that hypotenuse is congruent to the lower triangle's hypotenuse SRO, since it's the same hypotenuse. We also have another leg. PO, the radius here, is congruent to RO, which is the radius here. So, by the hypotenuse leg congruence shortcut, we know that these two triangles are congruent. Well, if two triangles are congruent, then we know that corresponding parts of congruent triangles are always congruent. That's this here. Therefore, we then can prove that SP, this part of our tangent line, is going to be congruent to SR, which is this part of our tangent line. So we have proven that these two tangent lines are congruent to each other from the point of intersection to the point of tangency by using one of our triangle shortcuts. Let's go ahead and do an example using our property. In this example, we say that segment SK, so right in here, is x plus 4. We'll mark that. And segment SM, which is this segment here, is 2x minus 9. So what we want to find is the value of x. Well, given our properties, we know that these two segments are congruent to each other, so we can set up a relationship that shows that they are equal or congruent to each other. Then we can solve. We'll combine our x's together on the same side. These cancel. And we are left with 1x on this side minus 9 equal to 4. All right, we'll move the 9 over to combine it with the 4. And now we're left with 13 equals 1x, or x equals 13. And that is our solution. Let's look at a few more examples. All right, in this next video, you're going to watch two examples. One where, notice we have actually 1, 2, 3 tangent lines around this circle, and they all meet and have a point of intersection. So we can make conjectures or statements about the segments AD, AE, also EB, BF, and GF and GD. And you'll see that being done. In our second example, this is similar to what we just did. We have two tangent lines that are intersecting, and we know that these two segments are congruent. So let's watch the example.
Here we want to determine the perimeter of this triangle. So if we start at point A, segment AE would be congruent to segment AD. So this would be 6 units. Looking at point B, segment BE is congruent to segment BF. So the length of BF must be 4 units. And then considering point C, segment CF is congruent to segment CD. Therefore, segment CD must have a length of 7 units. So now we just need to add the lengths of all of these segments. Here we have 12, 8, and 14. So 12 plus 8 plus 14. It's going to give us 4, carry the 1. That'll give us 34 units as the perimeter of this triangle. Here's our second example. And again, if we consider point B, segment AB is going to be congruent to segment CB because they're both tangent to the circle and they share the endpoint B. So we can set up an equation to solve for x. 4x minus 9 must equal 15 since the segments are congruent. So now we'll add 9 to both sides. So we have 4x, this is 0. 15 plus 9 equals 24. Divide both sides by 4. We have x equals 6. And we can go ahead and check this. 4 times x, or 4 times 6 is 24, minus 9 does give us 15.
All right, let's look at our last example, example 4. In this example, we'll be looking at the inside angles. Notice that when we connect these two tangent lines to the point of tangency, we have a quadrilateral. 1, 2, 3, 4 sides. So if we think about all quadrilaterals, quadrilaterals have 360 degrees. So if we outline our quadrilateral here, we know that the sum of all 4 angles must equal 360 degrees. Well, all I see right here is 35 degrees. Let's look at the question. Line PR and PB are tangent to circle O, which we know because we can see the right angles. Solve for the central angle AOB. Well, AOB is just right here. So we are trying to solve for x. Okay, if we just have one measurement here, how can we figure that out? Pause the video and see if you can figure that out on your own, and then come back and we'll do it together. All right, well, hopefully what comes to mind is that if we have a right angle here, then we know we have a right angle here and here. Together, those form linear pairs. Well, if we take 360 degrees, which is the total degrees in all 4 of these sides, and we subtract what we know, so we subtract 90 and another 90 and 35, we should get x. Whatever's left will be x. When we do the math, we get 145 degrees. And we can check that answer by taking 145 plus 90 plus 35 plus 90, and we should still get 360 degrees. And that concludes our lesson today on properties of 2 tangent lines to a circle. So at this point, you should understand the properties of the 2 tangent lines to a circle and be able to solve problems using these properties.